Okay, let me just make sure here that we are actually live and people are listening to us.
That's the thing with all these things online, right? We don't know if people are actually there.
Yeah, but yeah, people are there and we are also live, so...
Excellent.
Okay, good afternoon, everyone. Welcome to Valongo Seminars. I'm Luan Ghezi. I'm a professor at Valongo Observatory, and I'm also the organizer of our talks, together with Ariana Cortesi and Douglas Brambilla. And today, I have the great pleasure to introduce you to Raphaëlle Haywood, which is a dear friend and collaborator. And I'm very happy to have her here to talk to us a little bit about observing the sun as an exoplanet host star. So Raphaëlle Haywood is a lecturer in physics and astronomy at the University of Exeter, and she hunts for planets that orbit other stars, the exoplanets. Before joining Exeter, Raphaëlle was a NASA Sagan Fellow at Harvard University, and she holds a master's in physics from Imperial College London and a PhD in astrophysics from the University of St. Andrews. In her PhD dissertation, she developed an innovative technique for determining the masses of exoplanets, which now sets the standard in the astronomical community. She currently advises NASA and the US National Science Foundation on finding Earth-like planets. So, Raphaëlle, it's a great pleasure to have you here, and the floor is yours.
Thank you, Luan. The pleasure's all mine. I just wish I could visit in person, but this is the next best thing. So let me share my screen. Right.
Oh, yes, everything. No. Oh, okay, almost there.
In the corner there. How's that?
Yes, that's perfect. Please feel free to go ahead.
Okay, thank you, Luan. Welcome, everybody. Hello, it's very nice to meet you. I'm going to jump right in. So I'm a stellar and exoplanet astronomer, and I'm going to give an intro that really motivates the exoplanet side of my research, which is why, I mean, ultimately I work a lot on stars and on the sun, and that's all to learn more about the exoplanets. And so for the first half of my talk, I'll be talking about exoplanets, and then I'll veer off to the sun and eventually to other stars so that we can go full circle to the planets that orbit them. So as I'm sure most of you know, recent observations over the last couple of decades, and especially in the last few years with Kepler and now TESS and loads of other missions, show us that there are more planets in our galaxy than there are stars. And this is enabling us to think about, to really address some questions that humanity has had for millennia now. And in the last 2 decades, we're really able to give concrete, observationally driven answers to these questions, to start tackling these questions. And the types of questions that many of us are driven by and that many of us wonder about are basically, are we able to find exoplanets in our celestial neighborhood, so relatively close to the solar system? And if we examine their atmospheres, what will we find? And so we're really at this point in time where the technological capabilities are enabling us to, in the coming decades, in this generation, the grad students in the audience, this is your generation, we're going to be capable of assessing their potential for life, for hosting life, these exoplanets that are in our celestial neighborhood. And the kinds of questions that we're going to be looking at and that we're beginning to tackle already are things like, what are the atmospheres of exoplanets made of? What kinds of planets are habitable based on their atmospheric composition and their bulk properties? And of course, there's the biggest question of all that we're all wondering about, which is there life on other planets beyond our solar system? So these are big questions, and to tackle big problems, I always think that we need to break them down into smaller steps. So here's what I've done. The steps to discovering life beyond our solar system, I've broadly split this big task into 3 steps. So the first one is that we need to discover these planets. So we need to discover the nearest small planets. So when I say small, I mean roughly Earth size up to Neptune size planets. So basically not Jupiter sized planets, more the sizes of the rocky planets in our solar system, and discover the ones that are nearest in our neighborhood, because they'll be orbiting the stars that are brightest, and therefore will have the most information about these planets. And for this step, we have a couple of space missions. Currently, we have the TESS mission, which is looking at the whole sky, and it's looking at the brightest stars to find these nearest and smallest planets. And also very soon we'll have Plato, which is going to look at thousands and is going to find thousands more of these small planets and help us understand their planetary systems as a whole as well. The second step, once we have discovered these planets, we need to confirm them, and we need to characterize their overall bulk properties. And that's the step that my research focuses on, and that I'll be talking about next. And once we have confirmed these planets, and we have their mass, their radius, their orbital period, the main properties of them, that enables us to tackle the third step, which is to pick the ones that will be most amenable to scheduling them on future missions that will look at their atmospheres, that will get observations of their atmospheres. So lined up in the next decade, we have the James Webb Space Telescope, which is going to launch next year and is going to look at the nearest and brightest planets, and it will be giving us very interesting information about their atmospheres, so it can detect methane and water, and that's going to be really interesting. It's going to there are observations of atmospheres that have already been made, for example, with Spitzer and the Hubble Space Telescope and ground-based telescopes, but JWST will take it to the next level. And then towards the end of the decade, so towards 2030, we're going to have the Ariel space mission, which is a mission from the European Space Agency, and it will look at 1,000 planets, exoplanets, and their atmospheres. So that will give us a much bigger sample as well to go from. So to confirm and characterize these exoplanets, we need to use an independent observation technique. And the most successful of these techniques for doing this is looking at the radial velocity of the stars. So basically what you're looking at here is it's showing you that as a planet orbits its star, it makes the star wobble slightly. And you can see the wobble because it creates a blue shift and a red shift in the light of the star. And so the spectral lines, the absorption lines, are being blue shifted and red shifted by a small amount, but an amount that can actually be detected very precisely with spectrographs such as HARPS North on La Palma in Spain, and many other spectrographs. There are loads that are coming online that are able to detect the amplitudes from, we're talking about planets with masses of 2 to 10 Earth masses. So not quite where the next generation of spectrographs will definitely be able to get Earth mass planets. And so one of there are 2 things that this method does is that, so first it confirms that there is a planet there. If the star is wobbling with the right amplitude and the right periods, then we know that the planet's there. And the other thing is that it actually gets you the mass of the planet, because it's directly proportional to the wobble that the planet is inducing. And this is very important because the mass of a planet is the planet's most fundamental parameter. It's its main property. It's the main input that we give to models of interior composition and structure of exoplanets. It allows us to figure out what the planet is made of, really. And also, going back to that step 3 in our search for life, the mass will actually, it's essential that we know it really robustly before we select planets to observe whose atmosphere we're going to observe. Because imagine if you have, there's a strong degeneracy basically between the mass of the planet, which gives you the surface gravity, and the composition of the atmosphere. Because if you had a really, really massive planet, for example, then your atmosphere would be really squashed, right? So first, that tells you if it's a really squashed atmosphere, it might not be thick enough that we can observe it with the James Webb Space Telescope, for example. And then the other thing is that if you don't actually really know the mass of the planet, then how do you know how much it's squashed? And therefore, maybe the atmosphere is made of very light materials or of very heavy metals. And you can't answer that question unless you have the mass, because of the degeneracy between these two things. So obtaining the mass precisely is really key to characterizing exoplanets. And it's more difficult for those smaller planets because they have smaller masses. And right now, this plot is showing you the state of the field currently in radial velocities. So you've got the mass, well, it's M sin I, but really for the purposes of this discussion, it's just the mass of the planet, and as a function of the publication date. And you can see that in the beginning, we were discovering these are the hot Jupiters that were being discovered in the 1990s. And as the spectrographs became better and more precise, we went down to lower and lower masses until about 2010, when we actually started plateauing. And this is a slightly outdated plot, but 2019 and 2020 are not much different to these last few years. And so, and that's not because of the spectrograph precision, because we know that we have really precise and stable spectrographs. The main reason for this is because the stars that these planets orbit have magnetic fields and magnetic activity, and all of this produces noise in the radial velocity observations, even in the stars that are quietest. So often we think of our own sun as a really quiet star, and as you're going to see, I'm going to show you the data for the sun, and it's really not that quiet. At least it's not quiet enough for us to find planets with similar masses to Earth. So in order to determine precise masses of these small and rocky planets, we really need to understand the physical processes at play on the surfaces of the stars that host these planets. And the way that I'm tackling this with my collaborators in my work is to look at the star that we know the best, which is the sun. And I'm going to show you a few images to convince you that the sun is a really powerful way to probe these physical processes and understand them and model them better. Really, I think an image speaks 1,000 words, right? This is a photo of the sun from the Solar Dynamics Observatory, and in particular the HMI instruments, the helioseismic and magnetic imager. And it's just continuum intensity, so it's just white light in the optical. And you can already see many features of the sun's magnetic activity. First, you can see, well, the sunspots are jumping at you, but before we get to those, if we zoom in, you can see that there is a kind of, it looks like the image is pixelated, but that's actually a feature on the sun. And if we zoom in, that's the granulation. So it's a signature of convection. And basically you have hot fluid that is coming up, rising up to the surface of the sun. And as it gets to the surface of the sun, you're looking at these bright granules that are very bright because they're very hot, and they're very big because they're hot, so they're less dense, right? So the volume is bigger. And at the surface of the sun, the temperature is a bit cooler, so these big bubbles of fluid will cool down, and eventually, when they're cool enough, they sink in the intergranular lanes around the granules. And so you can see that the intergranular lanes look darker than the granules, right? And overall, there's less area of intergranular lanes because the material is denser. So you've got cooler and darker flow that's going downwards. And this is, I'm taking time to explain this to you because it becomes pretty crucial later on in the talk. So that's granulation. Then, of course, you've all recognized the sunspots, which are areas where you've got very strong magnetic fields that are cutting through the surface of the sun, and that's inhibiting this convective process. And so the fluid becomes cooler and just kind of stagnates a little bit. And so you've got these dark spots. And similarly, some of you may have noticed that you've also got these bright areas that you can see especially well on the limb. So these are faculae, and they're actually all over the disk. So they're not just on the limb, they're also in the middle. They're covering the disk pretty much everywhere. Now I'll show you that later as well. And so if we zoom in just to show you, these faculae are also magnetic flux tubes, and they're small tubes. And what happens is that they're not as big as sunspots, as the magnetic fields in sunspots. And so instead of cooling the surface, they actually heat it up through different physical processes. And what we're looking at, the way I like to think about it, is that you've got these tubes, and the walls of the tubes are the really bright, hot stuff. And so if you're looking in the center of the disk, say over here, you're looking straight through to the surface of the sun. So you're not actually seeing the walls, the bright walls of the tubes. But if you're looking on the limb of the sun, then you're looking through to the walls of the tubes. Okay, so that's why you can see them really well on the limb of the sun. So these sunspots and faculae and granulation, they all have effects in the radial velocity of the sun. And the way that I'm probing them is in my work is using these observations from the Solar Dynamics Observatory. And in particular, so we were just looking at a continuum intensity image. So it was a gray image, but this is just with an orange color scale. It's the same thing. And in addition to a continuum intensity, the HMI instrument on board the Solar Dynamics Observatory gives us a Doppler image. So in each pixel, it gives you basically the velocity, the radial velocity, so the velocity in your line of sight for every pixel. And again, you can see this orange peel pattern, which is, it's caused by the granulation of the sun. So it's not because the image is pixelated, it's actual physics. And another image that it gives you is the magnetic flux, the magnetic field. So this is a magnetogram, and you can see the magnetic regions they map, right? So you've got magnetic field of opposite polarities, right? So the framework that I'm using basically puts these images together so you can basically sum up all the pixels in the Doppler image and weigh them by the continuum intensity to get the radial velocity of the sun as a single point, the disk integrated radial velocity. And then you can play around you can select the active regions or leave them out with the magnetograms. And this technique was originally developed by Nadège Meunier and collaborators for SDO's predecessor, SOHO. So we use these images and we reconstruct the radial velocity according to a model. which has two components. And I'm going to talk you through those now. And then after that, I'll show you the comparison to actual radial velocities of the sun. So first, this is the model that we use. So there are two contributions. And the first one, which is the more intuitive one, is that you have the star and it's rotating. And so the half that's coming towards you is emitting blue shifted light, and the half that's going away from you is emitting red shifted light. And if you have a homogeneous surface, then the Doppler shifts just balance out, okay? But now if you have a dark spot on the side that's blue shifted, that's coming towards you, then you're getting this imbalance. So you're getting more redshift. And then as the spot or the dark feature or the inhomogeneity crosses the disk, as the star rotates, you get a radial velocity perturbation. So this is like the Roster-McLaughlin effect for planets, if some of you know that. And this effect produces radial velocity variations of about 0.5 meters per second, or maybe a bit less, depending on the size of the spot. So that's already an order of magnitude more than the signature of an Earth-like planet. But this is not the biggest effect. So the next effect that is really important, and I'm going to show you the observations to back this up, is it has to do with the granulation. So remember, I was talking about this image, these observations, and you've got the hot fluid that's coming up in these granules. It's coming up towards us, so it's emitting light that is blue shifted. And then as the fluid cools down, it sinks back in the intergranular lanes, and that is emitting red shifted light. But because you have this imbalance in the brightness, the blue light is brighter, the granules are bright, and the granules take more area, overall you have more blue shift. And so we call this the convective blue shift, and every star has it. On the sun, it's about 200 meters per second. So that sounds like a really large number, but actually, if it didn't change, if it was just a constant 200 meters per second all the time, then it would be fine. We could just look for the variations induced by the planets and it would be fine. But when you have magnetically active regions that cross the disk, like sunspots and faculae, then they're suppressing the convection. And so you're suppressing some of that convective blue shift. And that results in radial velocity variations of several meters per second. And I'll show you that in a moment. So this is the really annoying effects that we need to account for if we're to find planets. If you're on an exoplanet hunter, if you're a stellar astrophysicist, then this is really exciting. So we have these two effects, and we can model them using these high spatial resolution images from the Solar Dynamics Observatory. And at the same time, we want to compare them to direct observations. And so this is what I was able to do in the last few years as part of the HARPS North team. And what we've been doing is we've got the sun. The sun is so big that it's spatially resolved on the sky, but we have been able to, what we want to do is just look at it as if it were a distant point-like star that has no planets orbiting it either. And what we've done is, here is the HARPS North spectrograph. So this is the high accuracy radial velocity planet searcher in the Northern Hemisphere. It's at the TNG, the Telescopio Nazionale Galileo. And at night, it observes, it does Kepler follow-up. Currently, we're doing test follow-up of those super Earth-sized to Neptune-sized planets to determine their masses. But during the day, David Phillips and his team have installed a tiny telescope on the side of the dome, and there it is. And it's automated, and it's looking at the sun every day when it's not cloudy. And so the telescope scrambles the light of the sun so that the sun looks as if it were a distant star. And then we can actually, using NASA ephemeris data, we can remove the orbit of all the planets that orbit the sun. So including Earth, including Jupiter, all the asteroids, you can remove all of that. You can do barocentric corrections such that the sun is kind of like a distant point star. And when we do that, these are the observations that we obtain. So here you're looking at the radial velocity variations at a few meters per second as a function of time, and we're looking at about 3 years of data on this plot. We do have a little bit more now. And what we are doing is that we're taking an observation every 5 minutes. So there are actually over 26,000 observations just on this plot. And this is the sun without any planets, with the error bars on each of the points is about 0.5 meter per second. And yeah, that's what it looks like. So, so it already, you can see on the y-axis that you have about, well, you have excursions up to 8 meters per second peak to peak for the sun, which we thought was a relatively boring star. And you can also see the RMS overall is about a couple of meters per second. So if we plot the amplitude of an Earth-like planet, so if we take one Earth mass and we put it at a 365-day orbit, this is what it looks like. So you might have to zoom out a little bit to convince yourself that this is not a straight line. This is a sinusoid with a 1-year orbit. So this gives you an idea of the challenge that we're facing, right? We need to model all of these variations from the star, from the sun, in this case, in order to detect the Earth mass planet. Okay, so let's zoom in. Let's look at a few rotation periods. Now, this looks much more interesting to me, at least. You can see that you have quasi-periodic variations, and they roughly, so that's because the sun rotates. It rotates about every month. And we see, so we see the rotation period, and we also see a lot of half of the rotation period because you have multiple features on the sun, on the solar disk. And again, you have peak-to-peak variations of several meters per second. If you look at, this is a single day's worth of observations. So you see this scatter within a day of about 1 meter per second or 2 meters per second. And that's caused by the granulation. So the granules are going up and down, and you have millions of granules over the full disk of the sun. And so that's creating some kind of flicker that creates this scatter in these points here. Right, so now zooming in, well, if we take daily averages, so what I've done here from one to the next is just average down the granulation into single points. This is what we get. And the work I'm going to show now is work that has been done and published by Tim Milbourne, who is a PhD student at Harvard University and is going to graduate very soon this year. And so what he did is that he wanted to see, he actually did his analysis over the full data set, the 300, 400 days, the 800 days, sorry. But I'm going to show you the zoom in because it looks much clearer. So he modeled, he fitted these Harps North observations with the model that I described earlier that uses the spatially resolved observations of the sun. And this bit of the plot shows you what you get. So you do get a fit that looks reasonable if we look at the residuals. So overall, it follows the variations. If you look at the residuals, you do see some correlated residuals, some extra residuals. So you already have a hint that probably there are other effects that are at play that are not accounted for in our model, which only accounts for 2 different physical effects, right? But it does a reasonable first approximation job. And I've just included the RMS that you get from, that you expect to have from granulation and supergranulation, which is just granulation at large scales. And that's about 1 meter per second. So you're always going to expect scatter within that level. And what we found from this study is that Tim was able to further pinpoint what physical processes are really at play. And he found that the suppression of convective blue shift, again, is definitely the strongest, the major process at play driving these variations. And furthermore, you found that the bright elements, so the faculae, remember those small flux tubes, they're primarily responsible for suppression of convective blue shift. And I'm showing them in this image. So every red point all over the image, every one of those is a faculae. And you can see the spots in blue. But what you notice is that you have concentrated regions of faculae, and those are known as plage. And the rest, the less concentrated areas, are called the network. So what we found is that the plage are really responsible for the majority of the radial velocity variations through suppression of convective blue shift. So doing this, studying the sun in this way, because using these spatially resolved observations allows us to understand what's going on the surface and what is resulting in radial velocity variations, which, when we're looking at other stars, are preventing us from characterizing and even discovering small planets like our Earth. So a recent project that we've been working on is using these solar observations, the same framework, to see if we can identify a good indicator for a good tracer for these radial velocity variations. And that's what I'm going to show you here in the last few minutes. So again, we've been using observations from the Solar Dynamics Observatory, the same model that I was showing you previously. And what I'm going to show you here is that we took all of the observations from the Solar Dynamics Observatory. So SDO has been observing the sun since 2010. So it's got 10 years of observations now, and I'm showing you about 8 years here. And again, we've got radial velocity variations on the y-axis as a function of time. And you can now see the magnetic cycle of the sun. It's 11-year cycle. And you can see the characteristic double bump that we expect because the 2 hemispheres are peaking at different times. And also just for scale, this bit here is the same amount of time that Tim used in his work that I just showed you just earlier. So effectively, we've compared these observations, this time series, against HARPS North observations, and we've validated our framework, give or take the correlated residuals. And so we are assuming that we can just extrapolate this model to the full magnetic cycle. So that is one assumption. But this is also, this magnetic cycle looks, our reconstruction looks similar to previous work for a previous magnetic cycle, which is reassuring. So we know that from Tim's work, we saw that the magnetic elements, the faculae, are really responsible for these radial velocity variations. And it's been known for a while that the magnetic flux should be a really good proxy for radial velocity variations. So what we can do with these images, we can take the magnetograms and we can actually reconstruct the full disk magnetic flux of the sun, because we can look at the magnetogram and you can see the active regions. They have opposite polarities, and so if you were to look at any other star that you couldn't image directly, the opposite polarities would just cancel out and you just wouldn't see anything. But with the sun, because we can see the pixels, we can take the absolute values of the magnetic field in each pixel. So we can unpolarize the magnetic fields, and we can just add them all up together over the whole disk and get the full disk unsigned magnetic flux. And this is what I'm going to show you next. So again, at the top, we're seeing the radial velocity variations, and at the bottom, you're seeing the simultaneous magnetic flux variations. And you can see that they follow each other really closely. And if we do a simple correlation between the two, we get a very good correlation coefficient. And if we do a simple linear fit, so if you just take the magnetic flux and do a linear fit to the radial velocities, we find that we reduce the scatter in the radial velocities by about 60%. And we get down to below 1 meter per second. So starting to be in that range where we just expect granulation and supergranulation to dominate. So this is really exciting. There are a couple of caveats, but before I get to that, I'm going to show you, so if we reduce the radial velocity variations using the magnetic flux like this, and we inject planets, we are able to recover small planets. So here I'm showing you a phase plot. So you've got the orbital phase and the radial velocity variation folded for a planet that has a 30 centimeter per second amplitude at an orbit of about 300 days. And we detect this at, I think, the 5 sigma confidence levels. And if we do recover these kinds of planets. These are not quite like Earth just yet. If we want to get to 10 centimeters per second, which is the amplitude induced by an Earth mass planet in an Earth-like orbit, we do find, in agreement with Tim's study, that we need to model additional surface processes. So the residuals in here, in this plot, do show some correlation because there are other physics. So for example, there might be horizontal flows on the surface of the sun and other effects that we're not accounting for. And another important thing to mention is that we do not yet have the capability to measure the unsigned magnetic flux to the same level of precision as I'm doing here for the sun in other stars that are like the sun. So we need to develop techniques to measure the magnetic flux in slowly rotating and relatively inactive stars. And the following authors have got a good start on that. So it looks as though, so Annelies Mortier and Oleg Koshukov and collaborators, they're using Zeeman broadening. And they're getting to precisions of about 200 Gauss, which is still an order of magnitude more than a sun-like magnetic flux. So there's still much work to be done, but this work that I'm showing you really motivates the need to do these Zeeman broadening studies in order to measure the magnetic flux. And if we're able to measure it on other stars, then it's going to really help us understand what's on the surfaces of these stars and what their magnetic activities are like. So just wrapping up quickly, to know their planets, to know planets and their atmospheres, we need to know the mass. It's the most fundamental property of a planet. And to know the masses, we really need to know the stars that these planets orbit, because that's really the magnetic activity is the main obstacle that we face now. The instruments are good enough, but our knowledge and understanding of the physical processes at play on the magnetic, on the surfaces of the stars is really needs to improve by an order of magnitude. And my colleagues and I have been using observations of the sun from SDO and HARPS North to better understand the surface of the sun. And we found that the radial velocity variations on the sun are dominated by these large, bright regions of plage, so concentrated faculae, through suppression of convective blue shift. And hopefully in the future, the unsigned magnetic flux will be a really good proxy that we can hopefully measure in other stars like the sun. And that will get us a step closer to finding other Earths. So I'll take questions. Thank you.
Okay, thank you, Raphaëlle. That was an excellent talk. Thank you very much. It was really great to see all this interesting information, because we've been talking a lot about detecting other Earths around solar-like stars, and we can see that's not that simple. So we are talking a lot about biosignatures and everything else, but we have to do some basics before getting to that. So thank you very much for the excellent talk.
Thank you. You're welcome. Yeah, actually, that's something I didn't say, but this stellar activity problem, when we're looking at the atmospheric observations for these planets, it's going to be contaminated by stellar activity as well. So we're always going to need to understand the stars to a very high level of precision.
That's a very important point. So the saying, the exoplanet community, right? And so know the star, know the planet. So yeah. Okay, so we have some questions here in the chat, so I'll post them here and say them too. So you tackled this a little bit. So Gustavo, he's a professor here at Valongo. He works with, he's an expert in detecting solar twins and works with astrobiology too. So he wants to know about the solar RV variations. So you showed an expanded plot for the variations in the sun, but I think by the time he asked this question, I think he was referring to the first plot. So about the first plot that you showed, the observations on the sun, were they taken during a solar minimum, the last one that we saw?
So they were taken near solar minimum. If we look at the plot,
let me put this here.
Yeah, they were taken here, right? So the beginning was still a bit active, but actually right now we're really at the very solar minimum, and the sun hasn't quite started to be more active yet, and so it's really it doesn't have any spots, but it still has faculae. It still has a coverage from faculae of 2-3%, I think. And we still see an RMS and RV variations of maybe 1.5 meter per second. So it's still quite a lot. Gustavo, did you work on Coro 7? I think you did. I think I recognize your name.
So sorry, what?
I think Gustavo worked on Coro 7, which is my. I have a love-hate relationship with that star. I worked on it during my PhD.
Let's see if Gustavo. So Gustavo, please tell us if you work with Coro 7. So please let us know. Meanwhile, we will move to the next questions. It's Gustavo too, but a different one. So he wants to know: have you found stellar cycles by measuring the radial velocities?
Yeah, there are several papers that I could send you their references. For example, Ati Motalebi has published a paper in 2015 about so at Harps North, we have the Rocky Planet sample, the Rocky Planet search. So we've got about 50 sun-like so GKM stars, and we're monitoring them over the long term, and they found cycles in RVs. There are also, I mean, the CKS sample, the California Keck survey, I think they're also picking up cycles, not systematically. I mean, it's pretty much like in the Mount Wilson survey, where so they were monitoring the photometry and the calcimation K, and they find that some stars are cyclic, but some others are not. So definitely an ongoing, interesting investigation.
Okay, great, thanks. So Gustavo said that he did not work with Corot 7, but in the Corot program. So.
Oh, okay, all right. Thank you.
Okay. Okay, so moving on to the next question, we have a question from Aline. She's a PhD student working with me in planetary atmospheres. So she wants to know a little bit more about other difficulties to do the same analysis in other stars, and what could you do to help to improve the analysis?
That's a great question. There are lots of things that could be done. I'm thinking about, I think there are many ways to answer your question. I'm going to say that we're starting to really see, so with this solar data set, we've gotten 5 years of data with Harps North now, and the analyses that we've done show that there are processes, like physical processes, that are not, we don't know about. And so we need to understand those and model those. So for example, you have, I briefly mentioned, basically around sunspots and active regions, you have horizontal flows, so flows that are tangent to the surface of 50 to 100 meters per second. And so when these flows, you know, when the spot is on the edge of the sun, of the star, when it's coming towards you, it has the strongest radial velocity shift, and that could be producing, we suspect that's producing significant meter per second radial velocity variations. So, and on other stars, we know that they tend to have bigger spots than on the sun. So that could be an even bigger problem, right? There's another thing, I mean, how the granulation impacts the radial velocity is a whole field into itself. People like Heather Segler, Dana Dravens, and others are doing magnetohydrodynamic simulations, like 3D simulations of small boxes on the surfaces of stars of the sun, to look at how the granulation impacts radial velocity. There is that. There are meridional flows, some large-scale flows that act over timescales of years, that act on the solar cycle period, that produce meter per second, several meters per second radial velocity variations that could be mistaken for Jupiter's. But we barely know anything about meridional flows in RVs on the sun. There's one paper that's been published by Nadège Meunier in 2020. And for other stars, I mean, how are we going to identify those? Absolutely. It's a really, what's going to help a lot is going to be adequate sampling. So we need observations of stars every night for 10 years. And that's going to be given to us. Yeah, it's a lot. It's expensive. And even if you're looking at, you know, processes over months and years, the consensus is that you still want to really take observations most nights, because if you don't sample the process, then it just looks like noise, right? And so the Terra hunting experiment, which is being built and is going to be commissioned in the next couple of years, will be observing about 40 to 50 stars every night for 10 years. It's going to be with the twin of the Harps and Harps North spectrographs. at the Isaac Newton telescope on La Palma. So, and also the US has many spectrographs. It has NOID and Express. So more observations that are high cadence.
Great. That connects to a question that I had. So what do you think is the most pressing issue on the field right now? Is observations or theories?
It's a combination, really.
It's 50-50, right?
Yeah, the thing is that we can learn a lot from existing observations. I mean, the solar data set, so I didn't say, but it's been made, the first 3 years are public now. So if you go to Geneva has the DACE platform, the data analysis something planets, exoplanets. So you can go and get those radial velocities, and that's a unique time series to really probe the physics, right? And so we do have data sets, at least for the sun. For other stars, we have a few stars. I mean, Alpha Centauri B, for example, has, you know, multiple seasons that are well sampled. But we do need more data sets like these for other stars. That's right. But really, there was a recent working group that I was part of with many experts who we were basically advising NASA and the US National Science Foundation. Oh, you mentioned that, Luan. And we kind of agreed that really we need to make progress in the stellar physics in the next few years.
That's a good point, because people usually take stellar astrophysics for granted. So we know everything about it, so we don't know lots of stuff. Okay, so moving on to the next question. It's a question from Douglas. When comparing with the sun, how does the superficial properties of the star can affect the granulation and their influence in the radial velocity?
Yeah, well, stars of different sizes and different densities will have different sizes of granules. So, for example, I mean, my point of reference is always G-type stars, but if you look at F stars, which are bigger, you can work through basic equations of structure, which I will not do now. You can actually find that you get bigger granules on those. You get bigger granules, the star is bigger, but when it averages over, you have fewer granules because they're bigger. And so overall, you get more of that flickering noise. And we saw that in photometry. There's a breakthrough Nature paper by Fabienne Bastien in 2013 that shows you that you can see the photometry flickering over timescales of a few hours, and that's because of those big granules. And when you go from the F stars past the G stars and down to the small M dwarfs, those have tiny granules, and they have loads and loads of granules. And so overall, the noise is a lot less because it averages down much better. And you can see that also in Fabienne Bastien's work and others. And you can see it in the radial velocities, but again, the sampling of the observations isn't quite good enough to really see it. So absolutely, the basic properties of stars affect granulation, and it impacts radial velocity.
Okay, thanks, Rafi. So this connects with the next question we have here from Ricardo. So he's concerned about how to make the way from the sun to different stars with different masses and stages of evolution. So are you thinking about this, or are you focusing on the sun? How are you doing this?
Great question, very timely. I'm more focused on the sun-like stars, so at similar stages of evolution, I guess. But I do want to go to K-types and M-types. The M dwarfs are super interesting for exoplanet studies because all the most amenable planets for atmosphere observations are going to be orbiting M dwarfs, and K stars are kind of the sweet spot for they have less stellar activity and radial velocities. So the Terra hunting mission will be going for K stars. So I do want to extrapolate to that, and I will be hiring a postdoc very soon to do that. So if you're looking for a postdoc, stay tuned.
Well, so please, people that are watching, stay tuned, because there's a very good opportunity to work with a great scientist in a great field. So look out for it. And Rafi, if you forward to me this, I can forward to people that I know here in Brazil for the Institute. So
absolutely. And if you're thinking about it, if it sounds interesting, just apply. And get in touch with me. You're very, very welcome to get in touch with me too.
Okay, great. So going back to a question that Gustavo asked, it kind of connect with a question that I previously asked. So he wants to know a little bit more about what's the sophistication, what are the details that we need to work on, and how far are we in the sense of trying to detect make very precise detections of Earths around solar-like stars?
That's a big question. Well, if I take the example of the unsigned magnetic flux, right now the papers by Annelise Mortier and Oleg Koshikov and Lisa Lehrman, which are kind of doing the state-of-the-art, most precise unsigned magnetic flux measurements, they get about 200 Gauss precision, and sort of that's the kind. They measure unsigned magnetic fluxes of about 200 Gauss. And what we really want is, we want an order of magnitude better, or maybe 2 even, because the sun has 20 Gauss peaked. I mean, it has variations from 5 to 20 Gauss. And ideally, we want to measure that with, well, I'm going to say Gauss precision, but ideally, we want better than Gauss precision, because you want to get, I mean, you can back it out, right? Because you want sub-meter per second precision, and for every 1 meter per second variation, you have about 2 Gauss variation. So that gives you an idea. And the overall goal is 10 centimeters per second, although I feel like that's really on paper. We're not going to get that just yet. We're far from that. In the next 5 years, I think we're going to model those, those horizontal flows, and maybe a little bit better those meridional flows. Well, those meridional flows, they're a long time scale. We're going to need to wait for a decade for the observations. But we are going to get to probably 0.5 meter per second and better. But getting to 10 centimeters per second, it's going to take a lot of effort. But NASA has its eye on that now. We have brought attention to that, and they currently have a call for funding for postdocs, though the deadline is in a couple of weeks. So although you only have to submit a letter of intent, so it's not very much. But and then the full proposal is in a couple of months. But they're going to have, I think, much more funding coming up for this, for characterizing stars. And a big difficulty is, it's logistical. We need to get observatories to coordinate observations to get the high cadence observations for stars, and the long-term observations too, over multiple years. We need 10 years of data to find another Earth. And then the other challenge is, again, financially. This is a pretty multidisciplinary area of astronomy, because you need to, you can't just put in a proposal that's about exoplanets. It has to be about the stars and then possibly the sun. And so that's been falling through the cracks a little bit, possibly. So hopefully NASA is going to help us fix this. So it's going to take a lot, but it needs to be treated like a space mission would be. It's a big endeavor.
Okay, thanks. So we have another question here from D. Rodriguez. So he wants to know more a little bit about the atmospheric turbulence. Does this affect the measures that you do for the sun? And then he comments that he believes that it would impact the trending of the RVs, and asks if you could comment on that.
Yeah, thank you. I haven't actually mentioned that, but that's very important. Yes, so there is a paper that you might be interested in by Andrew Collier-Cameron that came out last year in 2019, and they do all of that detrending. and so you've got the fact that the sun is it's a large object on the sky. It's spatially resolved, and so when we're looking at it, for example, when it's setting, you might have the atmosphere is thicker towards the horizon, and then as you go up in the sky, it gets less thick, and so you get this differential extinction disturbance of meter per second level. You also have a problem when you if it gets a little bit cloudy. I mean, when you have a star, it just covers the star and you can't see it anymore. You know very quickly if your observation is good or not. But with the sun, if it covers just a little bit of the sun, then it's going to change the radial velocity, but not quite so much that you might not think it's normal. So cutting out clouds is a big deal. And the atmospheric extinction, the differential extinction across the solar disk is definitely has taken a lot of work to remove. Yeah. And it does increase the scatter when measuring solar activity. Great question.
Okay, thanks. So that brings us to the end of the questions, and we now have 1 hour, so we can start. Let's see. Oh, there's another question here.
Mm-hmm.
Oh, sorry. There is a little bit of delay, so I got 2 other questions, if you don't mind. So Eduardo congratulates you for the talk, and he says that it's supposedly better to look for inactive stars in the minimum of the activity cycle. So what's the best way to quantify their actual activity level?
So Eduardo, you touch on a somewhat sensitive issue because, well, if you're looking for other Earths, you need 10 years of data. And so in that time, if it's a sun-like star, it's going to go through all the phases of its cycle, right? So in the past, people selected stars that were less active. They did that using the calciumation K emission in the calcium cores, which is a good traditional indicator of activity. It's not as good as the unsigned magnetic flux, but at least we can measure it now. So it's very useful. And so they chose the least active stars. But the thing is, if you do that now for a 10-year survey, it might be, very inactive when you start, and then all of a sudden it just goes crazy. So we're now, as part of terra hunting, we're advocating for not doing these kinds of selection criteria, just picking, okay, it's active, but it's a sun-like star, and it fits, because it's very bright and other things. So we're trying not to do cuts, and the calciumation K remains a very good indicator. The photometry doesn't always correlate well with the radial velocity because the faculae are not visible in optical photometry like Kepler and K2 and TESS. So I think for your second question, I would just stick to calciumation K for now.
Great, that's good news, because he just defended his master's dissertation here, and he worked with the calciumation K, so that's good news too.
Great.
It was a great defense, by the way.
Congrats.
Okay, so another question here from Gustavo. You mentioned that meridional circulation might influence on the RV, so differential rotation should influence too?
Yes, it does. The thing is about differential rotation is that with current observations, generally, we're not able to really identify it directly because the evolution of the active regions on the rotating disk, just the evolution of the spots when they come and go, and they come back at different phases at different parts of the disk, they create a signature which is very similar, which is the same as differential rotation. So typically, if you do a periodogram of your time series, so you're looking at either photometry or radial velocities, you'll see peaks at the rotation period, and you'll see multiple peaks. And often we're very tempted to think that that's differential rotation, but in most cases, I mean, there are some specific scenarios. For example, if the active regions evolve very slowly, then you could conclude that you're splitting in the peaks as differential rotation. But in general, actually, that is, well, I mean, differential rotation is there for sure, but it's also mixed in with the evolution of the active regions. But yeah, if we're going to look in very high detail, we need to know about differential rotation. And that's still very difficult.
Okay, thanks. So now it seems that was the last question, but I would like to show you lots of comments that we had here. So Day Rodriguez is thanking for the great talk. And Mariana also says the same. She learned a lot from it. And it's very timing because she's working with me and starting to work with stellar activity too. So thank you, Rafi, for that.
Excellent.
Gustavo saying that marvelous, inspiring talk.
Wow, thank you.
And we have Elielson too.
Oh, hi.
So congrats for the talk. And Iana too, saying merci. So, so you can see that people are very, very excited about the talk, and it's for me it was kind of expected because I know you and I know that you're a great astronomer, and I'm very happy to be your collaborator. And it was a big pleasure for me to be the host of this excellent talk that you gave to us. And hopefully in the future, you'll be able to visit us in person here, Rafi. So thank you very much again. Do you have any final words before we end the broadcast?
Well, thank you all for joining, and thank you for your excellent questions. That was really interesting. You got me thinking about some aspects of what I was talking about today. And yeah, Luan, the pleasure is all mine. And indeed, we will be. Luan and I are looking at supervising master's students together in the coming year and beyond. So absolutely, if you're interested in working with both of us, then definitely get in touch. Yeah, and I hope to visit Brazil again very soon. Luan and I are working on showcasing the Amazon rainforest as though it were on a distant exoplanet. So just as you can study the sun as a star, you can study the Earth as an exoplanet, and that's what we're doing. And you can see the Amazon rainforest in that, which is really exciting. So I definitely hope to visit soon and meet you all in person. Thank you, everybody. Have a great afternoon.
Great, Rafi, thanks. Would you allow me to share the link here in the chat from your talk at INPE that you talked about the placing the Earth in the astrophysical context? Okay.
Absolutely, yeah.
Okay, for those of you that were interested in our work about Earth in an astrophysical context and looking at the impact of Amazon rainforest, so please check the link that I post here on the chat. Another excellent talk by Rafi that she gave recently on INPE, so have fun watching this. Okay, so thank you all very much for joining us today. Thank you, Rafi, again, one more time. And I hope to see you all next week for our next seminar. Have a great afternoon. Bye-bye.
Bye. Thank you.